So we have already mostly derived this, but let's make a quick review. We have derived marginal distribution, that means given the values of u2, where several possible values of u1 are summed up. Similarly, equal to for -1 as well as for +1. Same thing for u2, and that gives us how to compute expected values of u1 and u2. Subtract those expected values from the actual values that occurs, square them, sum them, divide by number of observations, and you get their variances as 1 and 2. And the third step, which is in fact more important, and that third step is in fact how to compute the covariance between u1 and u2. I have shown here the complete derivation of that. What do you mean by covariance? Remember the formula that we have for x and y, summation xi yi minus n times x bar y bar, something analogous to that. So how do we compute covariance between the potential error term values, which are u1 and u2? u1 takes -1 as a value, u2 takes -2 as a value. They occurring jointly, therefore their product multiplied by their joint probability 0.25. So -1 into -2 plus 0.25. But when u1 takes value -1, u2 can take value not -2 but +2. So again take this product multiplied by its probability. Similarly, when u1 takes +1 and u2 can take -2, this occurring as a pair has a probability of 0.25. So -1 into -2 into 0.25 plus u1 taking value 1, u2 taking value 2, multiplied by these two values occurring simultaneously 0.25. We compute this sum, and that sum turns out to be equal to 0, which you can verify, which means this 1 and 2 is a sigma 1 and 2 means the covariability of u1 and u2 is equal to 0. So u1 and u2 are uncorrelated. When u1 and u2 are themselves uncorrelated, we call the so-called zero autocorrelation. That means this is a situation where error terms are not correlated among themselves. So what we have done is we have the mean and variances of u1 and u2. We have also verified that u1 and u2 among themselves are uncorrelated. Now we have to also look at this problem of how to derive the sampling distribution of the proposed estimator. The proposed estimator beta hat is equal to summation xi into yi divided by summation xi square. As I have already pointed out, if you have got the correction factor concerning the means of both x and y wherever they occur, it will be same as OLS, but here there is no correction as it is there in OLS. So how do we derive the sampling distribution of this proposed estimator beta hat? So this is the proposed estimator of beta hat, and we want to see how it is distributed. From where is this distribution being generated? Distribution means frequency distribution. Various possible different values occurring. Why do they occur? They occur primarily because of the error term. From where does the error term enter here? Evidently, the error term enter here from y. So what we do is, we substitute this expression of y, and the expression of y of course is y equal to beta times xi into y. We don't know what this beta is. This is a population estimate, and the population parameter is beta, so we'll substitute that here. So see, we want to know this as a relation, which is a population relation, and we are going to estimate this beta, which is a population parameter, by this estimator, which we are going to apply to this sample at hand. And therefore, the question arises where, if we apply this formula to the sample at hand, and if we do this repeatedly for all possible samples, the value generated of beta hat from all possible samples, and if we take their expected value, does it coincide with the postulated population parameter beta? That's the problem. Okay, so we substitute that, and once we substitute that, what does it mean? It really means that we'll be writing it from this. In short work, we'll expand this, and so we are going to generate various different values of y. Values of x are fixed, so why there should be different values of y? Because the y contains not only x values but also it contains the error terms. And the error terms is not going to have unique values, there are more than one value. In our case, more than one means only two values. So in that case, we will be required to calculate all possible values of y that could be generatable, that could be generated out of all possible values of ui that are known to be occurring with their respective probabilities. So we are going to be required to therefore various values of y need to be calculated on the basis of beta hat plus ui from x1 equal to x2 and a joint distribution of u1 and u2, which we have already seen. We already have the knowledge of their expected values and variances. We also know that their covariance among themselves, that means between u1 and u2, is equal to 0. So what we will do now, we will substitute all possible values of x that are given together with all possible combinations of u1 and u2 values that can occur, and each of them with respective probabilities. And it is this probability come x weighted, that means it will get multiplied by x as well. As you can see here, there is the x which is standing outside. It is going to interact and have a product with u, and that's where the question of summation xi ui, that means error term and the x term being independent, actually arises. So let us see what it really means. So we are trying to derive the beta hat distribution. What is beta hat? This is the formula, this is the estimator. And as we had said, there is some unknown beta which relates x to y. That's a population parameter, but we don't know that. And we are going to be interested actually in beta, but we can't directly observe beta. So what do we try to do? We try to guess the estimate, construct the estimate of it using some formula, using some estimator. And this is our estimate. And this is the unknown, unobserved, but desired value of population parameter that is contained there in y. So we substitute the expression of yi equal to this, in this, which gives you xi into x beta. It is not beta hat, it is beta, unknown population parameter, plus ui. So this gives you, multiply throughout by xi, it gives you xi square into beta plus xi into ui under summation operator. So if you operate summation operator on the first term with the same divisor, then on the second term and the same divisor, so we can write it like this. So the first term operated divided by this will be equal to summation xi square into beta divided by summation xi square. Second part of this expression would be summation of xi ui divided by summation xi square. As you can see, beta is a constant, so I can write it in front of the summation operator. So I can write this term like this, and then what you get is beta times summation xi square divided by summation xi square, and naturally this cancels. And the remaining term is summation xi ui divided by summation xi square. So what remains is beta hat therefore is equal to beta times beta unknown population parameter, and this term summation xi ui divided by summation xi square. We know values of x1 and x2. So what will be the values of summation xi ui? We will later in a minute substitute these u1, u2 values because they are not 1, they are in fact in each case there are 2. So we have to consider all those possible values. But the general expression wise we will say that x1 times u1 plus x2 times u2 means x1 is equal to 1, so 1 into u1 plus x2 is equal to 2, therefore 2 into u2. Therefore this expression summation xi ui is in fact equivalent to u1 plus 2u2 divided by summation xi square, but summation xi square is 5. Therefore this ultimately results into the expression such as u1 plus 2u2 divided by 5. So if we have this as an expression, what is it that we desire? What we desire is, if we substitute all possible values of u1 and u2 with the respective probabilities, In this expression and compute and sum all those probabilities. If they turn out to be 0, what we will get? We will get is beta hat would be equal to beta, which is effectively saying that when summed over all possible error terms, the expected value of beta hat, all possible error term means all possible samples, because the error terms occurs in all of those samples. So all these sample error terms are going to exercise the impact such that the expected value of beta hat, when summed over all and that is taken over as an expected value, will turn out to be same thing as the unknown population beta. Okay? So let us find out what this u1 plus u2 divided by 5 gives us as a result for the known values, possible values of u1, u2 and their probabilities. So now that we are required to find out essentially the formula that we had arrived at, where beta prime was equal to beta plus summation xi ui divided by summation xi square. But as ui can take several values, in our case 2 values, which both u1 and u2 can take 2 values, and xi are fixed, that is x1 equal to 1, x2 equal to 2, we have to compute all combinations. Implicitly, when I am writing u1 plus 2 u2, it is actually x1 equal to 1, x2 equal to 2, which is implied here. But u1 and u2 can take several possible values in combination. u1 takes minus 1, u2 takes minus 2. So in that case, what do I get? I substitute this value here and here, I get minus 1. Similarly, u1 takes minus 1, u2 takes plus 2, then in that case the value would be plus 3. u1 takes 1, u2 takes minus 2, the value would be minus 3, and u1 takes 1, u2 takes 2, u1 plus 2, u2 takes 5 values. So for this expression summation xi ui, there are 4 possible values, and each possible of these values, given the probabilities, the joint probability associated with them with equal to 0.25, what we are required to do is in fact minus 0.5, minus 5 into 0.25, plus 3 into 0.25, minus 3 into 0.25, plus 5 into 0.25. Evidently, as you can see, these are the same values but with opposite signs. Their sum multiplied by the same constant will also be 0. Therefore, these are the 4 values, each with the probability 0.25, and thus we have summation xi ui for all possible ui's occurring will be equal to 0. Therefore, this expression in the numerator, or here, the numerator is 0, therefore divided by 5 will also be 0, which shows that therefore beta hat is equal to b. So see what we have done. We have considered all possible combinations of the values of the error term that can occur in conjunction with the known x1, x2, x3, xn value and so on, and then we substituted that, and then we find that unknown parameter beta hat over all possible samples, because it's now over all possible random values, are going to be same in the sense of expected value. Therefore, we can say that expected value of this expression coincides with beta hat. In this sense, we can claim that beta hat, which is in fact an estimator different from the OLS estimator, is unbiased. Though it is not same as OLS, but it is unbiased. So this is one part of deriving what is meant by deriving distribution of the proposed estimator, where the proposed estimator differs from the OLS in terms of absence of correction factor for the mean in both numerator and the denominator, but it turns out to be unbiased. Having shown that beta hat, which is the proposed estimator, which differs from OLS but for the correction factor for mean, is an unbiased estimator of unknown population parameter beta. Now, let us compute what the variance of beta would be on the basis of this estimate. Now that is going to be therefore proportional to the variability of error terms. But the error terms, each of them, you may notice, is getting multiplied by x1 and x2, and please note, this is getting squared. So it is divided by 5, because summation xi square is equal to 5, x1 plus x2 whole thing 5. So it is expected value of this as a variable square is the variance, and if we do that and substitute the very same expression that we had derived from u1 plus 2u2, which is minus 5, minus 3, plus 3, plus 5. Each of them occurs with the probability of 0.25. Therefore, we take these possible values, square them, multiply them by 0.25, which is the probability of their occurrence. And please remember, there is a phi in the denominator, which is also getting squared. Therefore, it is 1 divided by 25. And if we do this arithmetic, we get the value equal to 0.68. Therefore, we can say that variance of beta estimated on the basis of beta hat as an estimator like this can be demonstrated to be not only unbiased estimator of beta, but our estimate of variance with this as an estimator is going to be 0.68. So, I leave it as an exercise for you to find out what OLS variance would be, because OLS estimator refers to this. So, if you use the knowledge of OLS estimator and compute variance using the same machinery of computation, what kind of variance does it appear, and check whether that variance happens to be lower than 0.68.